Welcome, everyone! Today, we are going on a fascinating journey, deep into the memory of our applications. We're going to explore how software remembers things, all the way from these rigid, grid-like databases of the past to the really cool, intelligent systems of today that can actually understand meaning.
So let's kick things off with a simple question, but one that really frames everything we're about to discuss. In the world of software, what do you think is an application's absolute biggest fear? It's not bugs, it's not slow code, it's not even getting hacked. Nope, it's something much more fundamental.
It's amnesia, the total, complete loss of its memory, of its state. Because think about it, an app that can't remember anything is basically useless. So persistence, which is our big topic today, is all about building in resilience. It's the strategy we use to make sure that our data lives on, long after the program that created it has shut down.
Right, so as architects, our very first job is to design for survival. We have to work under the assumption that things will fail, and we have to build our systems to withstand those failures without forgetting everything they've ever learned.
And these are basically the three horsemen of data loss. First, you've got your standard process shutdowns, for planned maintenance. Then there's memory exhaustion. This is where the operating system itself just decides your app is being too greedy with RAM and poof, it's gone. And of course, the big one, a power outage, which instantly wipes out everything in that super fast but totally volatile memory. These are the very real threats we're always designing against.
To fight this threat of amnesia, we lean heavily on databases. And a really good way to think about a classic relational database is to picture a giant parking garage. Every single piece of data, every object in our code is like a car. And that car has to be parked in a very specific, numbered stall. That's our database row. And that stall is in a specific section of the garage. That's our table. This rigid grid system means we can always find any car, any piece of data just by knowing its exact coordinates. It's predictable, it's reliable.
Okay, so we've got this super reliable parking garage for our data. Awesome. But there is a huge problem. And this is the challenge that has been at the very heart of software development for decades. It's the reason our code and our databases often feel like they're from two completely different planets speaking two totally different languages.
Now on the surface, the translation seems pretty straightforward, right? A Java class, which is the blueprint for our objects, maps neatly to a database table. A field inside that class, like a username or email, becomes a column. And a specific object, like an actual user, becomes a single row of data in that table. Easy enough.
Well, what happens when our objects aren't just simple little data containers? What happens when they have these rich, complex relationships, kind of like a family tree? See, in languages like Java, we have this powerful idea of inheritance, where one object can be a more specialized version of another. How on earth does our flat, grid-like parking garage handle that?
And this slide right here, this shows the problem perfectly. Let's really slow down and look at this. In our Java code, it's natural to have a generic player class. Then we can create more specific types, like a footballer that is a player, but also has its own special attributes. This is a hierarchy. It makes perfect sense in our code. But the database, it can't think like that. It's totally flat. So to store this beautiful hierarchy, we have to tear it apart. We end up with a player table for the shared information. Then we need a whole separate footballer details table and another one for cricketer details. So now, if you want to get the complete data for a single footballer, the database has to do this expensive operation called a join. It has to go find the matching row in the player table, find the matching row in the footballer table, and then stitch them back together. Every single join adds work. It adds overhead. With complex objects, you could be looking at dozens of joins, and that can create a massive performance bottleneck that just grinds your whole application to a halt. This is the object-relational mismatch.
This little joke just nails the cultural divide here. The programmers are thinking in these fluid, connected objects, while the database people live in this world of rigid, structured tables. For a very long time, bridging that gap between those two worlds was a really painful manual effort.
So how did we finally solve this mess? Well, the Java community came up with something brilliant called the Jakarta Persistence API, or JPA. Now listen closely, because this is the most important part. JPA is not a tool. It's a specification. Think of it like the official blueprint for how a car engine should work. It's the set of rules. Then you have tools like Hibernate. Those are the actual engines built to follow the blueprint. And this is an absolutely genius architectural decision because it means we can write all of our code to this one single JPA standard. Then, if we decide we don't like our Hibernate engine anymore, we can swap it out for a different one, like Eclipse Link, without having to rewrite our entire application. It gives us freedom, it gives us portability.
Okay, so let's build on that. Now that we have JPA to handle the translation, we can start modeling the actual connections between our data. We can start building out this kind of social network living inside our application.
And really, these relationships break down into three main types, which are super easy to understand with some simple analogies. You have one-to-one, like a person and their passport. One person, one passport. Simple. Then the most common one-to-many, like a mother who can have many children, but each child only has one biological mother. And finally, you've got many-to-many, like students and classes. A student can be in lots of classes, and a class has lots of students. Now, when we define these relationships, we also have to think about their life cycles. By default, most relationships are what we call aggregation. It's a has-a relationship. Think about a student and a course. The course has a student. But if the course gets canceled, the student doesn't just cease to exist, right? They can go sign up for another course. The child can exist independently of the parent. But sometimes we need something much stronger. We need composition, which is a part of relationship. And the best analogy here is a house and its rooms. A room is fundamentally part of the house. If you demolish the house, the rooms are gone too. Their existence is completely tied to the parent.
And what is so incredible about JPA is how easily we can enforce this really deep architectural concept. To change a loose has-a relationship into a strict part of relationship, we just add this one little setting, orphan removal equals true. And just like that, if we remove a room from the houses list in our code, JPA now understands that this orphaned room should be completely deleted from the database. It's an incredibly powerful idea, enforced with just a single, simple line.
Okay, so even with all this powerful mapping and relationship stuff, we still need a safety net. What happens if the power goes out right in the middle of a complex operation, like a bank transfer? We absolutely need a rock-solid guarantee that our data will never ever be left in some broken, half-finished state. That guarantee is called a transaction, and it's built on 4 principles we call ACID.
These are the 4 sacred pillars of data reliability. They are non-negotiable. Let's walk through them, because each one is critical. We've got atomicity, consistency, isolation, and durability.
Let's start with atomicity. This one is simple. It's the all-or-nothing promise. The entire group of operations you're trying to do either succeeds completely as a single unit, or it fails completely, and the database rolls back to the state it was in before you started. There is absolutely no in-between.
But like with any technical principle, we have to ask the most important question an architect can ask. So what? Why does this actually matter for the business?
And here's the answer. It is our #1 defense against data corruption. Atomicity is what guarantees that a system crash can't leave your data in a broken state. It's what ensures money doesn't just vanish during a bank transfer because it won't let the credit happen without the debit. It is the absolute bedrock of trust in our data.
So for decades, that relational grid and those ACID principles, that was pretty much the whole world of data. That strict, predictable reliability was everything. But with the rise of AI, we're realizing that while the grid is still essential, it's not always enough for these new, modern workloads. We need to think beyond the grid. And this leads us to what has become the golden rule for AI storage. It's a very common mistake to try and stuff huge files, like videos or massive text documents for an AI model, directly into the database as something called a blob, a binary large object. This is a total disaster for performance. The right way to do it, the proper architectural pattern, is to store the small, searchable metadata about the file in your relational database, but host the actual huge file itself in a dedicated cloud storage service, like Amazon S3.
This shift in thinking has given rise to a whole new kind of database, one that's built for AI. Your traditional SQL database is like a dictionary. It is phenomenal at finding exact matches. You ask for the word apple, it takes you directly to the page for apple. But vector databases work on a totally different principle. They find semantic similarity. They don't care about the exact letters, they care about the meaning. It's less like a dictionary and more like a library of flavors, where the concept of honey is shelved right next to sweet and sugar because they are conceptually related, not because they're in alphabetical order.
And this new capability enables an incredibly powerful workflow for AI called Retrieval Augmented Generation, or RAG for short.
The best way to think about it is like giving an AI an open book exam. So instead of the AI just relying on its old training data, a user asks a question. The system then instantly searches a vector database for the most relevant, up-to-date documents. The database sends back just the specific snippets of text that are needed. And finally, the AI, the large language model, combines the user's original question with this brand new context to give a super accurate, timely, and much more reliable answer.
So, wow, we have covered a huge amount of ground here. We've traced this entire evolutionary path from the really manual, difficult work of managing data in grids all the way to this new world of automated mapping and now true semantic intelligence. Let's quickly wrap up with the key takeaways.
This table really sums it up. At the base, you have JDBC for that raw, manual SQL control, great for special cases. Then you have ORM and JPA, which automate that object-to-table mapping and are the workhorses for most enterprise apps. NoSQL databases give us that flexible model we need for big data. And finally, vector databases are unlocking semantic search for this whole new generation of AI applications. Each one is a specific tool for a specific job.
And that leaves us with one last big question to think about. For so long, reliable data meant exactness. It meant ACI compliance, perfect matches, zero errors. But as we start building these new systems that search by meaning, by concept, by similarity, how is our very definition of what makes data reliable going to change? What does it mean for data to be correct when the system cares more about how an idea feels than how it is spelled? It's a huge question and one we're all going to be figuring out together. Thanks for joining me on this explainer.